welcome to the first of a series of videos aimed at assisting with basic understanding of interesting facts in mathematical investigations. We'll begin with a look at arithmetic sequences. Carl Friedrich Gauss was one of the greatest German mathematicians of our time. When he was just 7 years of age, his schoolmaster asked him and his fellow students to find the sum of the first 100 counting numbers. That means 1 plus 2 plus 3 and so on up to 100. To the amazement of his fellow students and his teacher in particular, Gauss found the answer very quickly, almost instantaneously. But how did he do that? What Gauss did was to mentally split up the 100 numbers into two sets of 50. So we write the first 50 numbers, as you can see, and the remaining 50 numbers from 51 up to 100 we can write in reverse order, like so. Then Gauss paired the numbers in this fashion. So the first pair sums to 101. The second pair, 2 plus 99, also sums to 101, and so on. So we can see that what we have are 50 pairs of numbers, each of which sums to 101. And that means the total sum will be 50 times 101, which is 5050. Let's have a look at another arithmetic sequence that we can use to develop properties. We have our sequence 3, 5, 7, 9, and 11. What we notice is one of the basic properties of an arithmetic sequence, which is that the sequence of numbers either go up or down by the same amount. In this case, you can see that the numbers go up by 2. The first pair gives us 5 minus 3, which is 2. The second pair of consecutive numbers is 7 minus 5, which is 2, and so on. We can refer to the first term of our sequence as lowercase a, so we can write a equals 3, and the value for which the numbers go up or down, in this case going up by 2, we refer to as the common difference, and we use the lowercase letter d, so we can write d equals 2. Let's look at this one. We can work out the common difference. In this case, you can see that consecutive pairs of numbers give us -3, and the first term will be 9, a equals 9, and of course the common difference, as we said, will be d equals -3. We can generalize in order to obtain formal relationships, so let's begin by calling our first term, which we said we can refer to as the letter a. We can also refer to it as T1, T meaning term, so we have T1 equaling A. Then our second term will be T2, and that will equal A plus D, because our second term is the common difference added to the first term. We then have T3 being A plus 2D, and so on. And our last term of our sequence we can refer to as Tn, where n is the nth term. And you can see that we can represent it by a plus in bracket n minus 1 times d, just following the pattern that we can observe. So we can write that down as the nth term of an arithmetic sequence being Tn equals a plus n minus 1 times the common difference d. Let's apply that basic property to this example. What is the value of the 50th term of the sequence, 100, 96, 92, and so on? We begin by writing down our formula, Tn equals a plus n minus 1d. We need three values, one for the first term a, one for the common difference d, and one for the value of n, the term that we are looking to evaluate. Our first term is 100. The common difference is -4 because the terms are decreasing by 4, and n will be 50 because we are looking for the 50th term of the sequence. So substituting those three values into our formula, we have T50 equals 100 plus in brackets 50 minus 1 times the common difference -4, which gives us a value of -96. So the 50th term of that arithmetic sequence is -96. We will now obtain a relationship that gives us the sum of a given number of terms of an arithmetic sequence. As you can see, the first row contains our arithmetic sequence. A is the first term, A plus D the second term, and so on, all the way to the nth term, which is A plus n minus 1D. Underneath that, we can write our sequence of terms in reverse order. So our first term of our second line becomes A plus n minus 1D, and so on. And then, just pretty much as Gauss did, we can pair the terms, and that's what those arrows represent. Our first pair of terms will sum to 2a plus n minus 1d. Our second pair of terms will also sum to the same value. Indeed, so will all the terms. So what can we conclude from that? We can say that two lots of our series of terms for an arithmetic sequence consists of n lots of 2a plus n minus 1d. And from that, we can say that the sum of our sequence of terms, which we can represent by capital S subscript n, is equal to n over 2, and then in brackets, as you can see, 2a plus n minus 1 times d. So that's our formula that will give us the value of the sum of a given number of arithmetic terms. Now let's see if we can apply that to what Gauss did remarkably quickly in his own mind. We have our arithmetic sequence 1 plus 2 and so on up to 100. Our first term is a equals 1. Our common difference is 1. And the number of terms we wish to add is 100, so n equals 100. We have our formula for the sum of an arithmetic sequence. We substitute our values for a, d, and n, and you can see that the sum is indeed what Gauss did mentally, which is 5050. Thank you for watching this video. I hope you found it both interesting and informative, and I'll see you soon.